So this was going to be about math, but everybody's already done all my math for me. So this is going to be more about some of the math, only a portion of the math, and some of the ideas, because I think there have been a lot of really interesting conversations. The hallway track, the dinner track last night, etc. And lots of ideas have come up, and I've taken pages and pages of notes with little squares drawn next to them for me to check off when I've actually looked into those things and satisfied myself or decided to dig deeper or whatever. So lots of stimulating thoughts and conversations, and I just wanted to weave some of that in here because, like I said, a couple of people, you'll figure out who have already talked about some of my talk. So just briefly, who I am, I've written or contributed to some stuff and written a lot of open source software. And a couple of years ago, I founded VividCortex, and we do database performance management, software as a service. You can think of it as New Relic for the database, probably the quickest way to say that. And all of our APIs and agents are written in Go. Our front end is in Angular because we're hiring. So we had a really interesting dinner last night, very thought-provoking. Somebody tweeted today, what would happen if Adrian Cockcroft and Neil Gunther got into a room together? And Paul Dix and I had dinner with the two of them last night. And interesting things happened. I learned, for example, of contributions to the Voyager project, among other things. But while I was there, I tweeted, I'm the farm boy. I do have a computer science degree, but I'm a farm boy. I thought this was fun and worth sharing. So the big question about a lot of time series metrics that we've been seeing during this conference is talking really about anomaly detection or what is typical. And I'm going to go off on a couple of different rants. I'll try and tie it back together for you at the end. But the big question that everybody's really asking about with anomaly detection is what is typical? Anomaly being another word for something not being typical. And I want to talk about some of that stuff, but first, because squirrel, I want to talk a little bit about my worldview. And this is the first time I've been to Monitorama. I really wanted to come to the others, but I had already been committed to things during those times. And I was really surprised to hear people kind of saying bits and pieces, and taken together, it kind of fits into my worldview. I don't think of VividCortex, and in fact, I explicitly say we are not a monitoring company, and I left Percona after many years to found VividCortex, specifically with the idea in mind of not building a monitoring tool. What people have been asking me for years was a monitoring tool. But I don't think that monitoring tools go far enough. So let's categorize monitoring really quickly as health checks and metrics and graphs. But usually the metrics and graphs part of it, for example, is kind of, I'll take all the metrics that you throw at me, they're dumb numbers, I don't know what they mean, I'll draw strip charts for you. Those are just going to be some visualizations. There's no particular meaning or model associated with them. There's no underlying worldview of those kinds of things, and I wanted to build opinionated tools that knew things about the systems. And so the unifying principle of what I am doing, that is why I say we're doing performance management instead of monitoring, is that the work getting done is really the first principle for us. And we're talking a lot about things like math and tools and so forth here today, but I also wanted to build something that was a complete solution and not just recipes, not for example, something that would allow you to arbitrarily apply functions to your metrics and see what the result is, but something that knew what those metrics mean and show you something meaningful, apply the right functions to those metrics for you and show you the results. This does tie into anomaly detection. Some of you have probably heard me talk about something called adaptive fault detection that we invented. And fault detection is not the same thing as anomaly detection. A fault is when a system's not getting its work done. Again, they focus on work getting done. Anomaly is when something is unusual or abnormal. And there's a big difference between those things. Also, there's kind of a lot of things that I feel get conflated together when we talk about things like anomaly detection. There's, for example, somebody, I don't even remember who now, but somebody in the hallways yesterday said the phrase, using Holt-Winter's prediction for anomaly detection. Well, Holt-Winter's prediction is a prediction technique, but it doesn't have anomaly detection built in. That's something that gets layered on top of Holt-Winter's prediction. All of those things built on top imply a statistical framework, as I say here. So an anomaly is, when we say that an event or a metric or a measurement or something like that is outside of the norm, anomalous, we can only say that with some level of certainty. It's not 100% certain, it's not a Boolean true or false. It is evaluated against some statistical framework that assigns a probability, usually, assigns a probability to how unlikely that was to have occurred. And so all of those things I think need to be sort of treated separately and recognized separately in order that we don't get confused about what we're talking about and kind of do things wrong. So that concludes my talk, not really. So now that's kind of some preface. I just wanted to set my worldview for you. So the thing about anomaly detection that's kind of often looked at as the holy grail, and I have an asterisk here because this is not really, full disclosure, I don't spend very little time thinking about anomaly detection. I thought about anomaly detection because there are two different types of anomaly detection that are embedded in our fault detection algorithm. That was a long time ago, and I haven't really seen any need to improve it since then. So the whole thing that we kind of seems to be the holy grail that we might be looking for is to understand how a metric normally behaves, understand how a system normally behaves, use that to predict the future, and then quantify how far your measurements are this time period from what you would have predicted last time period. So that is the whole basis of anomaly detection. It's all done in a framework of prediction. So that's really core to what we're talking about here. And then hopefully we can do useful stuff with that. We do our metrics in 1 second resolution. At 1 second resolution, you will find that your systems are just unbelievably anomalous all the time. And if you want to alert yourself on that, a quick little bit of math here. So there's 36, and I'm just doing this off the top of my head, 3,600 metrics, at 1 second resolution, you're going to get 3,600 measurements per hour. And we're capturing just sort of from the operating system and so forth, we're capturing a couple of thousand metrics from the system. So if you have 6 sigma anomaly detection, that's roughly 2 events in 1,000 are going to be called anomalous, assuming that everything follows Gaussian processes, and 6 sigmas represents 99.7%. So that's 2 in 1,000, so that's like 7 per metric per hour. So multiply that by some thousands, and you're going to have 7,000 anomalous measurements per hour from a typical systems. And that's not even, we're not even talking about measuring the queries that go into a system, which is one of the major things that we do. And I'll show you a slide later where we show you how many time series metrics we actually get from systems. It's not a couple of thousand, it's tens of thousands. So that's why I'd say that anomaly detection is not necessarily the holy grail that you might think it is if you actually look at systems in fine detail, which is what's most useful to do in my opinion. So I'm going to go and play with a little bit of math. Unfortunately, Tufik stole a bunch of my thunder. Gunther stole a bunch of thunder. Everybody is stealing all my thunder. But what they kind of did, though, was they started at the beginning and then they jumped to the end and said this stuff doesn't really necessarily solve all of your problems. And I think the process in the middle is still interesting. So that's what I want to talk about. And I will get to what the one weird time series metric trick is. So this is a screenshot from one of our features in our app. Everything is time series, and here you can see that we're collecting from this system, 50,000 plus time series metrics in 1 second resolution about queries alone. So that's a lot of data, and being able to process that data efficiently is really, really important. So a lot of the techniques that you might think about, let's say machine learning. Somebody tweeted about anomaly detection. The founder of OpsGenie was tweeting about anomaly detection. I retweeted a couple of those, and then somebody tweeted back to us and suggested Ted Dunning's talk on machine learning and anomaly detection. Ted Dunning from MapR. That stuff is all very important and useful, but it's difficult to do at scale, at fine resolution. So having efficient algorithms is actually really important and useful. Also being able to do things besides displaying strip charts is really useful. So these metrics that I'm showing here, those are all time series metrics. They're just not displayed as time series. And all of those things are in 1 second resolution, and these are for different parts of the system. So for example, I'm showing CPU time per query. The rows in this table are queries, individual families, classes of queries, and one of those columns is CPU. Well, CPU is a time series metric, and it actually is not measured inside the database server and cannot be. And there's a white paper on our website about the whole process of regression that we had to go through to get this. But we're taking a time series metric from one place and another unrelated time series metric and figuring out the relationship between the two of those and showing it to you as a width and a bar. So there's, I think this goes back to Neil Gunther's point about time series metrics not always being appropriate to display as a height going from left to right in a strip chart. So there's a lot of stuff that we can and should be doing with these metrics, in particular analyzing them much more deeply. And to do that, in many cases, we need to really focus on efficiency. Also back to Adrian's opening keynote, we have lots and lots of data. We need to be getting the answers out of that data, because if you don't get answers, all you have is questions that you haven't, I like to pose the sort of devil's advocate question, the so what question. If we haven't been able to answer so what, we have a spike in CPU, well so what? Then we haven't done the whole job. How many of you don't know at least one thing on this slide? I don't. There's stuff on that slide that I don't know. How many of you tried the Smirnoff test last night? That's one of my little squares that I want to look into later. And there was an interesting dialogue with Theo last night or yesterday about that and maybe some of the potential shortcomings of this test. Notice that I'm avoiding pronouncing it. Tongue twister. How many of you know all of the descriptive statistics and other types of statistics that are mentioned in the Wikipedia category on data collection and so forth, statistical inference, all of those kinds of things alone? I don't know what most of this stuff is. I am not a statistician by training, but I can still do useful work. Basic statistics is really good for a lot of things. You don't have to reinvent everything. Most of the basic statistical techniques that exist are actually not really being applied in our field. Somebody mentioned earlier about Nagios flat detection. I had not thought about that as a low-pass filter, but it is, and that's a great point. They reinvented something that works really poorly, and I think we all know that it works really poorly. Now we know why, right? It's because basic techniques of low-pass filters were not applied there. So you can do lots and lots of amazing stuff with basic statistics, and you can do it efficiently and simply as possible. Simpler is usually better as long as the underlying model actually describes your reality. And if you need advanced stuff, study it. It might take you a little while. We worked for about 6 months on that regression technique to show those little blue bars that I showed you. And learned a lot of pretty deep stuff, and probably came into contact with a lot of stuff that I thought that I learned and didn't internalize fully. And Neil's one of our advisors, so thanks to Neil for that. And don't let anybody tell you that you can't do this if you don't have a PhD, because I can't count the number of times that somebody has kind of put someone else down because they don't have a PhD or don't have an advanced degree, or just, in general, they're not good enough and they shouldn't be playing with this stuff because all they're going to do is cause trouble. That is completely opposite of my worldview. I say, follow your intuition. Where's Neil? Neil's in the back. Every time I say intuition, Neil corrects me and says, don't listen to the siren song of intuition. Tell me if I'm getting this wrong. Don't listen to the siren song of intuition. Chain yourself to the rocks of math, or chain yourself to the mast, or something like that, of math and science. But I think you should listen to your intuition and trust yourself and use the techniques that are available to you. So there's always this spectrum. There's this spectrum between trying to do really, really advanced stuff. This comes from Benjamin Black, by the way. I know I credited the URL there, but Benjamin Black, one of the people who helped invent EC2, among other things that we all rely on every day. So there's this sweet spot between, are we not even applying the basic techniques that we have, or are we doing super advanced, super geeky stuff that is probably well above and beyond what's actually needed? So let's begin at the beginning. At some point, I'm actually going to start my slideshow. So all of these things are built on top of each other. So the anomaly detection needs to have a model of what it means to deviate from normal. Deviation from normal can only be can only be derived by comparing against a prediction. Predictions come from generally assessing some central tendency or trend, and or possibly a combination of those things together. And that comes from some characterization of history. Okay, so all of these things need to be recognized separately, and there are potentially many different techniques that you can use at each level in this little sort of Maslow's hierarchy of needs. Here's that tweet that I was mentioning from the founder of OpsGenie. If you're out there, I'd like to meet you, by the way. I don't know if you're still here or not. Dumb systems are not going to produce good results. You need to actually understand what's going on. I fully agree with these tweets. Our fault detection algorithm, for example, is based on work getting done. I think we can probably all agree that if a system is getting its work done, regardless of whether something has gone wrong and healed or whatever, it's not faulty. If it's doing its job, it's not faulty. If it's doing its job and then stops for a little bit, our fault detection algorithm will catch that. So that's kind of our definition of a fault. So central tendencies. I'm getting to the one trick, I promise. We saw this yesterday in control charts. Notice that this chunk of data this is from a time series metric on real customer systems. Notice that you don't see like your daily trends here. That's because I'm focusing in on a window of the data. If we look at this over days and weeks, you can kind of unfocus your eyes and you'll see clear patterns in them. But when you start looking at really fine detail, that's when you start to see how anomalous things really are. So it's 900 data points here. And looks like 4 of them, 6, there's a whole bunch of them that fall outside of what we might consider 3 sigmas. I've drawn 3 sigma control chart lines on either side of the mean there. This doesn't technically work very well for time series data for reasons already mentioned. The stationary mean, most of the approaches to deal with this try and transform this data into something with a stationary mean. There was a little conversation right after Neil's talk where somebody was asking about, can you remove out the, let's say, daily and weekly variance and then consider what the data looks like with that trend subtracted? Well, that's what Holt Winter's prediction does, actually, is it transforms the data into something with a stationary mean so that you can apply these kinds of techniques against it. That is a model of anomaly detection built on top of Holt Winter's prediction, which is a model of prediction. And systems, it was mentioned yesterday several times. Most of the machine data that we'll get is not Gaussian distributed, not normally distributed, so it's not from the Gaussian process. And in that sense, it's not normal. Also, your systems are going to be constantly anomalous, as I mentioned earlier. So what we have then is necessarily the interest in looking at something that's recent, not at all of history. So the first idea, my first implementation years back, was just to look at a window of data. So here's the same data, and I'm applying standard descriptive statistics such as standard deviation and mean over windows. So in this case, it's a 60-second moving window. So you can kind of see, you can see these little 60-second periods, if you look at them correctly, in that data. So there's kind of a blockiness to this, but it does transform that stationary mean into a moving mean, moving over a window. And this is over a rectangular window, if you're remembering back to the fast Fourier transform talk. So we still get a whole bunch of outliers. We don't get as many. We have basically one big outlier kind of in the middle on the bottom. So that's better. It's a lot better, but it still has some problems. So the moving average is relatively expensive to compute compared to some other techniques because it requires you to keep that entire window and then to repeatedly recompute. There are ways you can optimize that, but still that's annoying and it's still not as efficient as it could be. And then the other thing is that the current value of your moving mean is influenced by what happened in the distant past. And here I've taken this metric and I'm showing the control charts as gray regions in the background shaded. And you can see that after a big event, like there was one big event right here, and our control lines were way far away from the mean until here. And then we had another spike here, and the control lines remained very far away from the mean for a while. Okay, so this is not particularly good because it means that when a spike occurs and then 60 seconds later that spike falls off of your window, you are going to unspike all of your metrics, and in the meantime you kind of equally weighted everything all along that window. So these were some problems that I encountered when I was dealing with this kind of stuff. And what I wanted to do then was to use exponentially weighted moving averages, which bias towards recent data, and they retain memory of all of the data theoretically to infinity, but in reality, with floating point numbers, we don't actually get that. And they're really cheap to compute compared to standard fixed moving windows. And all you need to do is, it requires just one variable. The entire history of that variable is encoded in one number. And all you need to do is choose a decay factor alpha, and then you just multiply your current measurement by alpha, and then you multiply the previous result by 1 minus alpha, and then you add the two together and you've got your exponentially weighted moving average. Okay? So it's a little bit easier to explain with pictures. So here's a time series, and a color-coded time series. So to begin with, there's many ways to initialize this. I'll just initialize to the starting value, and then I'm going to choose a decay factor of 1/2. So I'll multiply my previous value by 1/2. The gray bar gets half as big, and I multiply the current value by half and add those together. And then we continue to do that. And if you look at the tops of those bars, you'll see that we're starting to develop a central tendency here. And this is a very effective and cheap way to do this. So that's the one time series metric. But I'm not done yet because there's a bunch of stuff that you can do with this. So that's an exponentially weighted moving average, and it is a form of low-pass filter. It's a central tendency that's very cheap and much more, biased much more towards recent data than to distant data in the past. Okay? So you can choose your decay. I'll leave that for your reference. There's some other stuff that we can do, like making exponentially weighted moving control charts. So it's basically the same technique. We just need to figure out how to do exponentially weighted standard deviation. This is kind of sort of a minimal viable product version of that. And so then we get exponentially weighted moving control charts. You'll notice that our data point on the bottom here in the middle is still a little bit of an outlier, but not so much as it was before. So again, we're in all of these things, we're still applying a Gaussian model to this data. We're still applying an underlying framework, statistical framework on worldview on this. So if the data doesn't match this, like if this particular variable is Gaussian distributed, normally distributed from a Gaussian process, but if the data doesn't match that, then you will get terrible results. Still useful sometimes. So one of the ways where it falls down is when you have a trend. So I've generated a sine wave, and then I just added the sine wave, and then I transposed the sine wave upwards so that it would lie over top so you can kind of see where the bias in that data is. This is still the same data, but I've just added a sine wave into it. And then I added the exponentially weighted moving average of it. And what do you notice? It is delayed. It's phase shifted. So exponentially weighted moving averages tend to trail. The phase is shifted a little bit later than the signal. Okay, so it doesn't match up very well. And that's a shortcoming. So exponentially weighted moving averages don't do well on things that have a trend. It's okay if the mean is typically stationary, even if it's sort of wildly stationary. But when you get a consistent trend upwards or something like that, your exponentially weighted moving average is going to fall underneath of that trend consistently. So this gets into double exponential smoothing. And there's many different ways to do this. So if you look on Wikipedia or Wolf or Math World or whatever, you'll find different definitions. And it's because there's no one way to do this. So feel free to choose your preferred way of doing double exponential smoothing. But basically what you're doing is you're exponentially smoothing the data, and you're subtracting each data point from the one following it, and then getting the trend from that and exponentially smoothing that, and using that to predict how much up or down your data has been headed. So same thing. I'm now plotting the double exponential smoothing as well as the standard exponentially weighted moving average. But now you have a whole bunch more factors involved. You have not only your alpha decay factor, what's usually called a beta, which is the decay factor for the trend itself. And those things are actually very sensitive. So if you mess around with these things a little bit, you can get, I probably should have taken some screenshots and put them all on here. You can get the double exponential smoothing can way overshoot, or it can way undershoot, or you can actually get weird delay factors as well. So it's a little bit better, but it's certainly not perfect. So again, exponentially weighted moving averages. Now we've got two of them and we're combining them together. Next trick is Holt-Winters forecasting. So we take double exponential smoothing and we add in a seasonality factor. And this is a way, again, of transforming the data into a stationary or relatively stationary mean. I'm not going to show pictures of this because you've probably already seen it, and I was doing all of this in a spreadsheet and I got pretty deep into the weeds and didn't end up with something that I could show you, sorry. But it is, there's a couple of shortcomings with this. It's getting more and more complex. Now you have up to 5 things that you need to choose. For example, you need to know what the seasonality is and how many periods within that seasonality, and your 2 exponential smoothing factors, and what is the 5th thing? I can't remember. Anyway, there's a lot of things that you need to think about, and you're either going to need to know what those things are and tell the model, or you're going to need to do something really fancy, such as a whole bunch of linear algebra and linear optimization to figure out what the best fit for those parameters should be. And at that point, you need to start asking whether you're overfitting your data and all those kinds of things. So it definitely gets complicated pretty fast, and you get far off into the weeds. It's by no means a panacea. So the final trick that I wanted to show you is moving average convergence divergence. And this is the difference. A lot of these techniques, by the way, come from finance. So moving average convergence divergence is commonly used to tell whether a stock price is trending up or down. In general, statistics and finance, they're kind of worlds ahead of us. So you can always look at what's happening there. So we take 2 different decay factors and we generate our moving averages, and then you can just subtract one from the other, and that will tell you whether your data has been trending upwards or downwards recently. So you can see that one of these obviously has a much longer decay than the other, and so it's much more smooth. And it allows you to compare right now somewhat smooth to right now really smooth and ask whether you're heading upwards or downwards of that. So simple, just 2 moving averages and just subtract them, and you can get a trend in your data, even in really noisy data, to the extent that you trust that what you're doing is the right way to model your data. So I think, I don't have my presenter display on, so I don't know how I am on time. How are we?
You have 2 minutes for questions.
I have 2 minutes for questions, okay. If no questions, I have bonus slides.
Bonus slides. Can you see the bonus slides?
Yes, sir.
Have you tried subtracting your current data from the same time period, say the previous week, to create a delta that should remain close to 0, and then control charting that?
So the question is, have I tried subtracting current time data from a previous week to see how that works? Yeah, I've done a whole bunch of those kinds of things. One thing I'll tell you, any of these approaches like Holt-Winters prediction that look at the data and say the future ought to look like the past are very susceptible to things like, you had an outage and now you will expect an outage in the future. It can also take some time to train. So those kinds of things, they're a double-edged sword. Also, you need to assume or determine and tell your model that a week is the right period to be looking at. Or you might do weekly, hourly, and daily, or those kinds of things. And those things can take some time to train. As I mentioned, typically the sort of rule of thumb for Holt-Winters is that you need at least 2 and better 3 full cycles. So in the case of most of us are dealing with data that has a weekly seasonality, sort of the most obvious seasonality. You might think that it's hourly or daily, but if you look at Saturday and Sunday, those would be very different from Friday, which tells you that there's multiple seasonalities going on. So you will typically need at least 3 weeks of data for the system to settle and train, and particularly if you're if your data is kind of young, let's say you've brought up new servers and those servers, or you've changed something in your deployment and your servers are behaving differently than they did before, for a little while, you're not going to get very good results. Lunchtime? All right, lunchtime. Let's do it.